Hey again, method students. In this video, we're going to start to look at the distribution of the sample proportion. So really thinking of this, this p hat value, which is the proportion of a sample that have some certain trait, as actually being a variable, meaning that it's something that can change. So we have to kind of define p hat, or the distribution of p hat, as something that can vary depending on the sample that's selected. So for example, if we consider a population, so let's kind of simplify a little bit, let's consider a population of 20 people. So 20 people is like the whole population, where 5 members of the population are female, right? So we've got this population of 20 people and 5 of them are female. So in this context, capital N, which is the population size, is 20, and P, which is the population proportion, is 1/4, where P is the proportion of females in the population. If we were going to take a sample of 5 people, so little n equals 5, well, there's actually a bunch of different possible values we can get for the sample proportion. In other words, for the proportion of females in the sample that we choose. So for example, it would be possible that we could end up with a sample of 5, and I've kind of just circled like this little diagram. You could end up with a group of 5 people where there's none of them are female, right? So it's possible that we would get p hat equals 0/5, which is of course 0. So the sample proportion could be 0. But it would also be possible if we took a different sample of 5, and even if we're doing this randomly, you know, we got a different random sample of 5 people, we could get 1 female in that group of 5, and so that would be p hat equals 1/5, because the proportion of our sample that are female would be 1/5. It's also possible if we picked a different random sample that we could get 2 females in our group of 5, and so that would give us p hat equals 2/5. And I think you get the idea, but it's, you know, it's possible to go on and think about, well, we could choose a sample that ended up with 3 females in it out of this population. And so that would give us p hat equals 3/5. The sample proportion would be 3/5. We could get 4 females in a particular sample. And it's also possible that we might end up with a sample that has actually all 5 of the females in it. So it's possible that p hat could be 5/5 or 1, right? We could get a full, 100% of the sample could be female, depending on the sample that we choose. So the whole point of this example is just to think about this p hat value, the proportion of people you get in your sample is a variable. It can change, and it won't always stay the same from one sample to the next, right? So it might be like, you could randomly survey 10 of your classmates one day and find out that, like, I don't know, 20% of them are going to, 20% of them will buy their lunch from the canteen or something like that. Then the next day you might pick another 10 classmates and ask them the same question. You won't necessarily get the same proportion of people who are going to buy their lunch from the canteen, because you might get a different mix of 10 people when you take the next sample. So p hat is a variable, and that's a really key idea here. So when we go to work out, we've got a couple of sort of, or one formula here. When we actually go to work out the distribution of p hat, or more specifically, when we go to find the value of p hat, the value of the sample proportion, p hat, is just the number of successful outcomes in the sample over the sample size. Now that makes it kind of sound, you know, maybe more complicated than it is. All it is, right, if I go back to just picking one of these things from that previous page, this one here, we worked out that p hat was 1/5 because we had 1 female out of 5 in our sample. So it's just, you know, one number out of the total in your sample. It's a relatively simple formula to apply. If we sort of use notation, we could say, well, if x is the number of successful outcomes in the sample, then p hat would equal x over n, where n is the sample size. So if I just go straight to an example here, I think you'll see exactly how it works. If we let p be the proportion of all students who use the school canteen, and then this question says, well, we've surveyed, so out of 30 students surveyed, 22 stated that they use the school canteen. Determine the value of p hat for this sample. Well, p hat is just the proportion of people in this sample who say that they use the school canteen, which is 22 out of 30, which simplifies to 11 out of 15. All right, that's how you work out the sample proportion. It's a relatively straightforward formula to apply. Example 2 says for a particular sample, so this is a different question, p hat equals 0.4 and x equals 12. What is the sample size? Well, if we think of the sample size as being n, then we can actually just say, well, okay, our formula is p hat equals x over n. Putting in the values that we have, we've got 0.4 equals 12 over n. Therefore, n is going to equal, if we rearrange the equation, multiply both sides by n, divide both sides by 0.4, n will equal 12 divided by 0.4, and well, that's the same as 120 divided by 4, so that would be 30, n equals 30. Oops. All right, so that's just a little bit of practice with sort of applying this relatively straightforward formula for working out the sample proportion, right, this p hat value. Okay, this next little idea we'll cover off on it. It's good to talk about here. It's maybe a little bit more complicated than what you'll actually need to do with these questions, but it's again sort of still good for your understanding to think about this. So if we go back to this example that we did at the start of this video, where we had a population of 20 people, and here's that little diagram again with 20 people in it, and we were choosing a sample of 5 of them, And in this population, there were 5 females, right? So the population proportion, P, not P hat, but P, was equal to 1/4. And then we're taking this sample of 5 people. Well, when we think about all the possible values that we can get, we knew that we went through it and we said, well, we could get 0 females, we could get 1 female, we could get 2 or 3 or 4 or 5 females, depending on the sample we take. There's obviously more likelihood of each of these outcomes, more or less likelihood, depending on which ones are actually closer to a proportion of 1/4. So for example, it's very, very, very unlikely, given that there's 20 people here and only 5 females, the chances that you pick a random sample that actually gets 5 females, it's very, very unlikely, right? Like, it's possible to happen, but it's not very likely, because there's only really one way that we can do that, whereas there's thousands and thousands of other combinations that give us every other sort of proportion. So the idea here is that the sample proportion that's most likely to happen is the one that's closest to the population proportion. So if 25% of the population are female, in this example, well, it's more likely that your sample is going to be something close to 25% female. It's less likely that you'll get like 80% female or 100% female. And that's kind of what this table's showing you. It looks very complicated, but basically these are our possible values of the sample proportion: 0, 1/5, 2/5, 3/5, 4/5, or 1. These formulas are giving us all of the different ways that we could end up with a sample proportion of 0 or a sample proportion of 1/5 or 2/5 or so on. Now, we won't kind of get into too much detail about how these are worked out. You can see that with this sample of taking 5 people from a group of 20, there's 3,000 ways that you could end up with 0 females. There's 6,800 odd ways you could end up with 1 female. 4,500 ways of getting 2 females in the sample, just over 1,000 ways of getting 3, only 75 ways of getting 4, right? So that's getting quite unlikely, and then only 1 way of getting 5 females in this sample. So when you look at the likelihood of each of these outcomes, it's these, getting 1 out of 5 and 2 out of 5 that are much more likely than the others, okay? And that's because 1 out of 5 and 2 out of 5 are the proportions that are closest to what's actually in the population. So if we were to graph it, you can see that the probabilities, or the proportion of times these samples are likely to happen, the probability is much higher for those two, 1 out of 5 and 2 out of 5. And for all the others, it kind of tails away. The further away we get from the value of P, the less likely that sample is to happen. It's possible to happen, but it's less likely. All right, so just a little quick summary of I guess, what we've talked about here. Key point is that P hat, the sample proportion, is a variable, right? So its value can change depending on the sample that we actually take. P is a fixed value. P is a fixed value because we know that a certain proportion of the population have a particular trait. So P is a fixed value and P hat is a variable. And the other thing that's kind of important to think about, and we will come back to it in this next little section, but the idea of having a large sample. Now, this key idea here is that the larger the sample size, the better the estimate of the population, right? Now, that just kind of makes logical sense. If you've got a population of 1,000 people, and you ask 2 of them a question, well, you're not necessarily likely to get a really good reflection of the population. But if you have a population of 1,000 and you ask like 500 or 600 of them, well, you've asked a significant proportion of the people. So there's a better chance that that will give you a more realistic estimate of the population. So the larger the sample size, the better the estimate of the population proportion. And as the sample size increases, the sample proportion should become closer to the population proportion. Again, you can kind of just think of that sort of logically. Now, there's a few different ways of kind of determining whether you consider a sample size to be large. This sort of formula is one way. It actually appears in our textbook. There's a couple of others. It's probably not something that you necessarily need to know, so don't sort of worry too much about it, but that's just one way that you can actually work out whether a sample should be considered a large sample, so to speak. But I probably wouldn't pay too much mind to this one here, so I'll just flag that as one that it's there if you ever need to use it, but it's probably unlikely that one's going to come up. All right, I might split the next bit. We'll go through the second half of this exercise. It's a bit of a long one in a separate video, so I'll see you all in the next one.